Welcome. Today, we want to go over the details of the Niosh revised lifting equation. My name is Ryan Belikov, and we'll get going. So from this lecture, you should be able to describe when we're using the Niosh lifting equation, what are the 7 modifiers? So remember, 6 of those are lifting factors. And then what other characteristics come from a revised Niosh lifting equation as far as the 3 categories and the risk value? So this is paying homage to one of the creators of the revised Niosh lifting equation in 1993. So one of the main researchers was Dr. Tom Waters. He has since passed from a tragic bike accident, but I think it's very important to pay homage to him. So this picture comes from one of my mentors, Dr. Kilkey. He was at the Triennial, and these guys are some of the main influencers in ergonomic assessments. So just to go over a few, in the top left corner is Tom Waters here, dead center, Dr. Snook. Remember those Snook tables, early 80s, looking at push, pull, and lifting. We got Dr. Schäflin in the back, the SI assessment here, Dr. Cromer. So this came from the Legends. Dr. Gilkey was taking a picture during COVID. I had the opportunity to go to this conference and be a part of the Titans, but it was all online, so we didn't get a good picture, but this is a good one. So when it was published for the revised Niosh equation in 1993, the year following 1994, actually a substantial interest within the different fields took notice of the said Niosh lifting equation, much more so than the original Niosh lifting equation in 1981. So prior lecture, we went over the validity of the tools for the Niosh lifting equation. So it was recommended, and it gave a result of a recommended weight limit. So that's abbreviated as RWL. So from the results of this revised Niosh lifting equations, many sectors actually adopted it, but several, like the automotive industry, really clung onto it for a standard for the ISO, so the International Organization of Standards. And so this one that they attached to was 11.22.8-1, but there was definitely other sectors. So just to read exactly why they did the Niosh lifting equation, the revised one, they said this equation was designed to evaluate the lifting demands / characteristics within respect to estimation of risk of low back disorders. So this Niosh lifting equation is not a direct measurement. It is indirect measurements that characterize if there's a risk or not. Other than using the Niosh lifting equation, I really want you to come away with some of the limitations of when not to use the Niosh lifting equation. Number one is it was made for a two-handed material handling lift, so not one hand. Also, you'll see if pushing, pulling, carrying, walking activities account for more than 10% of that total activity, you shouldn't use this equation. If there's unpredicted conditions, so such as if you're in a mine where there's heavy trip hazards, that they did not apply, feel like this was a valid tool. And then not lifting while kneeling or seating, so only upright. And then adequate coupling factor. And then lastly, the Niosh assumes that the lifter and the lower have the same risk. So just things to really consider when applying this equation. So this is kind of a side note. So one of my mentors, Dr. Yoki, was looking at this, and his mentor was Dr. Boswick. both at Utah, but they were looking at doing one-handed lifts. And they saw very similar to the Niosh lifting equation where the horizontal distance really was the main modifier. So something to consider, and nice to see the connections there. As well as, again, this just goes into that percent likelihood of that one-handed lifts, looking at each of those odd ratios between the Niosh lifting equation and what they were looking at with one-handed lifts. So this is the revised Nash lifting equation. Notice that they have 6 lifting factors, but we start with load constant. So they're saying if all of these modifiers are 0, ideal conditions, not doing anything, the max you should lift is 51 pounds. And then each one of these modifiers actually take away. So this second one here is that horizontal distance. Remember, this is the moment arm, so most important one from the center of the body to where they're grabbing it at that second knuckle, how far distance it is, horizontal distance from the floor to where they're handling it, then the how far they're taking it. You can measure that. The twist is the AM component. So what's usually also difficult is when they give this equation for like the CIH, they won't give you HM, LM, DM times all of this. So you have it, but you have to know what they mean. So AM is a lifting one, so it's less obvious. The frequency is how many per 15-minute increments. The coupling is how you're grasping that object. So when we put all those together, the lifting constant times those 6 lifting variables, we get a recommended weight limit. So this is what is recommended, the RWL. And so we can get a categorize what is the risk value. So we do the weight of the whatever we're lifting, whether it's 16 pounds, 40 pounds, divided by our uh, weight recommended weight limit, and that gives us a value. So if it's equal to 1, it's good, but as it increases to 3, for example, would be a high risk scenario. So example here, with if we take the 51 load constant times what modifiers is given as 16.4 pounds for the recommended weight limit, what we're actually lifting is 25 pounds. So that 16 or the 25 divided by the 16.5 gives us 1.5. This is, probably a very mild risk value, just depending on the person, probably. You can make that judgment call. So when they did these, now we have iPhones that we can do inputs the modifier, but if we have measurements, we can use these tables with the revise. So this first table is that horizontal, so from the middle of the body to wherever we're grabbing. So for example, if it's 18 inches from the body, then we're saying that modifier is 0.56. And then we also have it in centimeters, depending on how far it is. Notice each one of these tables give also a centimeters and inches, to give you an example. And then down here, it's a little different by the coupling. Remember, if it has handles, it's good, so no modification. Fair would be able to grab it. Poor would be a kind of a slippery object or a bulky. So this is example we use for the students in the warehouse, looking at, they wanted to know if it was a high, medium, or low risk. And so we had students off to the side that you can see here. And they didn't do too many lifts, but they actually had a hard time keeping employees. So they want to look at these high risk lifting. And so the 3 categories, low, medium, and high. When we took the measurements, actually the students took the measurements. Again, we start with that load constant, 51 pounds, even though this is 44 pounds, I believe. The horizontal distance of this is a little trickier because they have a split leg here. So you go from that second knuckle where they're gripping it to the middle between those legs. So to the ground to measure, they measured 13. So from the ground to where they're grabbing it was measured at 18. The angle, they were saying they were twisted at 45, which is about halfway. For frequency, they weren't doing this very many times a day, and this doesn't have handles, but they're able to grip it, so they said the coupling factor was fair. So when we, oh, didn't proceed. So putting that into equation, that this is one of the examples that's on your modules, when you put those in, it gives you that revised lifting equation of 24. That pound actually lifting was 44. I believe it's a 1.2, but I have to do a calculator to know, so it's kind of a lower risk. So this is in your references, but this is from North Carolina. They did Excel to make it easier so you could just input that. Notice on the Niosh lifting equation, you do one action, measure the measurements for the origin and the destination. So one thing I like about this, North Carolina, they did a lot of color coordinating. So as you can see at the origin, that modifier of the horizontal distance from the middle of the body to the object is probably the greatest one at modifier of 0.77. And then it gave us a lifting index of 1.8. But notice the destination, that horizontal location is even worse at modifying at 0.45, giving us an index of 0.28. So between the two, that destination is definitely more. Um, So this comes from the revised Niosh lifting equations. So Niosh updated their pictures in 2024. Some of these are examples using the same examples, but just updated pictures. So looking at this example with the conveyor belt, so they're taking a box from the line, putting it in another box. So how far they're lifting, what's the height of that? Versus how far they're going. So let's put this into the equation. On this, we're saying that the load constant again is 51 pounds. That horizontal distance, 14 from the origin. So the origin from the middle of where they're grabbing it to the body is 14 inches. We're saying they're lifting for one lift per minute for 8 hours. The coupling is fair on this one. We're saying a twist of 90 degrees, so they're fully twisting their body at almost 100%. The vertical height, if we go for the origin, we're saying around 24 inches. So when we apply that equation, looking at these tables, that horizontal, we said 14, so the modifier is a 0.71. But for that vertical multiplier, it was 24, right? Well, there's not 24 on here, so we need to make a judgment call. On this one, we went a little safer and just bumped it up to 25, so that modifier is a 0.96. That distance they're traveling, uh, just a short distance, 20 inches, so a small modifier on that one. Their asymmetry, remember that 100% twist at 90 degrees, so 0.71. The frequency, not very many, only one per minute, but their shift is long for 8 hours, so 0.78. So notice on this frequency modifier, it depends on your shift, so less than an hour. If it's less than 2 hours, and then 2 to 8 hours, so that third category is often used. Oh, also on that frequency modifier, it matters on the distance. So we'll give an example of that. Again, there was no handles on that box, so a fair zero point 0.7. And this kind of goes over a word description, how they're using that coupling factor. So using that Niosh worksheets on here, if we input all of those, we get a recommended weight lift of 16.4 divided by the actual weight of that object was 25 pounds, so 1.5. So pretty low risk value on this example. And so that's just going over again what we just went over. So remember, Niosh lifting equation is just a tool. You need to put your industrial hygiene and make a judgment call. So on this example of 1.5 is a concern, is that, that package, is there been other problems in the factory about it? Does that person have other risk factors? All kinds of things that you should be considering, even in just going to like, oh, this is low risk. What else do you need to consider? So most important, consider that hierarchy of controls. So of course, elimination is our top one. If your company is millions of dollars, the elimination is a much easier target. So in this example, instead of a person packaging it, it's automated, right? So that would just eliminate that material handling altogether, but most places cannot do that. So they jump down here to administration controls. I often see these in larger factories that have thousands of workers where they're just changing those people over just to decrease that ergonomic risk. So again, on this example, the two big risk factors was that horizontal and the AM, which is that twisting. So if you address these two values, that recommended weight limit is going to go up and the risk value is going to go down. So a good way to apply this. And again, we have mentioned there's an app for the Niosh lifting equation for the revised one. Please go get it. It's free, it's easily searchable, and you can just input these numbers for both the origin and the destination. It will give you that recommended weight limit as well as which category it is for risk value. This is an example from Dr. Bernard in Florida, where you could put multiple origins and destinations on here to give you your recommended weight limit and lifting index. And then we did the example with North Carolina. I like theirs because it's very color coordinated. And please send me questions. I look forward to what you have. Lastly, I want to highlight a program we have here in the lab with the ErgoMaster. It's really oriented towards that L5 S1 compression, giving you values, but it also has the Niosh lifting equation. This is an example of lifting a 40-pound fertilizer bag, looking at that destination, looking at that index at 2.95, so pretty high risk, as you'll find most lifting things off the floor is pretty high risk there. And more a snapshot of that ErgoMaster, just what are the inputs and outputs that you want to put in there. So hopefully from this lecture, you're able to identify the differences between the revised Niosh lifting equation and the original one in 1981, how valid it is, when are we going to use it, what are the modifiers that go into this modeling. And then lastly, when we get the numbers, what are we going to do about it and what kind of risk is associated with it. With that, thank you